All right, folks, here we are. Now we're looking at the derivative and integral of bases other than e. So think about that as like, what's the derivative of 2 to the x? Now, something to note is that when we did e to the x and we took the derivative, it was the derivative of y equals e to the x. And what we did is we figured out it was just e to the x, but it's always times the natural log of your base as well. But the natural log of e is just 1. So what we're going to do for the derivative of a base that's different from e is it's going to be 2 to the x would be your first part, but then it's times the natural log of 2. That's the only difference between a base other than e. So that comes from the fact that when you do the change of base formula, which most of us don't need to use anymore because of our calculators, it's the log of the value over the log of the base. So you'll notice it's log of x over log of a. In this case, you could also do ln of x over ln of a. And you can see that when we looked at the values before, if I take the log of something, the derivative is 1 over ln of a times ln of x. So you can actually rewrite it as just 1 over ln of a times ln of x for that part. So this is just looking at change of base formula. That'll come in a little bit later. All right, so let's first look at some properties of exponential functions. So just a reminder, we actually went through this in our last set of notes. So what we hopefully remember is last time, if you have the same base and the same base in a log, these cancel, so you end up with x. You could also think about putting it in log form and it works the same way. Same thing with something like this. If you have log base a of a and you have it raised to the x power, think of it as really like x log base a of a. This is 1. Think about like log base 2 of 2. It's like saying 2 to some power gives you 2, and that's 1. So this gives you 1, so anytime you see that, it's to the x power. And it gives you x back. So solving for x in different log equations. We actually did this a little bit last class with base e, but now the properties are the same. Something you can do is put the first one in log form, or just think about exponent rules. So there's a few different ways to do this. You could either pretend like this is 4 to the x equals 4 to some power is 1/64. So 4 to the third is 64, but 4 to the negative third is 1/64. So x equals -3. You'll get the same thing if you put that in log form. So another way to do it, you don't have to do both ways, but I find the first way easier, is put it in log form. So we log base 4 of 1 over 64. That is not 64. That is 16. Sorry. 64 equals x. So that is putting it in log form from here to here. And then you could just put this in your calculator. You could do log of 1 over 64 divided by log of 4, and that's the change of base formula. Or a lot of you guys have the log change of base formula in your calculators. So actually, if you go to math on your calculator, and then you scroll down, a lot of calculators have a change of base formula in the calculator. If you don't have it, you can just use the change of base, which is, again, log of the value, which is 1/64 over log of the base, which is 4. So next one, I would put that in exponential form. So if you see something in log form, to get it out, put it in exponential. If you had me last year, you did seashell method. So 3 to the 5th equals x, because it looks like a seashell. So that is exponential form. And then you can just put it in your calculator, so x equals 243. The next kind is slightly more advanced, but you can actually solve both of those right now. If you want to do the first one together, just don't pause the video and I'll go through it with you, but the second one we should be able to do based off of what I did on the previous example. So the first one, I recommend dividing by 3 first. What's annoying is you kind of get a decimal here, but you can leave it as 86/3 just to be a little more exact. Then if you have an exponential function, you can actually put it in log form to get it to get the exponent away, when you take the log of something, it actually undoes the exponent. So I would do log, the base is 5, of 86 over 3 equals x minus 1. And then again, if you have that change of base function in your calculator, you can plug this right in. Or you could do log of 86 over 3 divided by log of 5, and that gives you the value. And then you would just add the 1 to both sides. So what you end up with is x equals 3.08, because the log of 86 over 3 divided by log 5 is 2.08. So you'd add the 1 to both sides. Then, for the last one, I want you to try it out. Pause the video. When you come back, it'll be done for you. All right, so hopefully you did exponential form. So 8 to the 2.6 equals x minus 3. Then you can just do 8 to the 2.6 in your calculator, add the 3, and you get 225.86. All right, next up, bases other than e in your graphing calculator. It says, use the graphing calculator to find the zeros. So if you don't remember how to do this, you plug this whole expression in, and then you figure out the zeros under second calc in your calculator. So in your calc, you would type this into y1, and then you could actually type in y2 as 0 if that's easier for you to find the intersection. The other way is, again, go to second calc after you've put it in y equals, and then there's a zeros option, and then you follow the directions on the screen. The other thing you can do is separate this a little bit, so you could separate the logs. You don't have to, but you end up with 3.826 and negative 0.826. So you end up with 2 different solutions. Alrighty, so derivatives where your base is other than e. What you end up doing is you rewrite the value of the base and the exponent, and then you take the natural log of the base. Again, like I said before, we did that actually with ln of e. If you remember when we had y equals ln, or 1, basically e to the x, right? The derivative ends up being e to the x, but times ln of e wouldn't do anything because that's just 1. So now we're just reiterating that rule. The only difference is when you have an exponent that's not just an x, right? You have to do ln of a, but times the derivative of that exponent. How we're used to doing it, not really new to us, very exciting. We also learned the derivative of ln of x is 1 over x, right? Except now, again, as like very similar to what we just talked about with a to the x, now you have to multiply by ln of a. Just be careful, it's in the denominator altogether. So it's 1 over x ln of a. And again, a is the base, no matter what. So same idea in the fourth one, which is log base a of u. As we're used to, you have to multiply by the derivative of whatever u is. So it's 1 over u ln of a, which is your base, times u prime. So you'll see what I mean in a second. Okay, let's take the derivative of y equals 5 to the x. That is right. You are correct, ma'am or sir. It is y prime equals 5 to the x times ln of 5. Done. Beautiful. All right. Next up, we have 5 to the 3x minus 5. So you end up getting 5 to the 3x minus 5 times the ln of 5, but then you have to multiply by the derivative of your exponent. So you end up with times 3. Now you cannot combine any of those together, so you just leave it. Or you can put the 3 in front if you really want to, but it can't give you 15. You can't multiply the base when it doesn't have the same exponents. All right, next, we need to take the derivative of 3 over 2, 3 to the 2t over t. So now, think about what your u would be. This is the tricky one because you have an extra thing in your denominator, okay? So this is going to require u substitution. Or you can use quotient rule, whichever one you would like to do. So I am going to use quotient rule. It gives you the same answer. So it's going to be my low d high times ln of 3 times 2, because that's the derivative of your exponent, minus high d low, which is 1, so times 1, all over low, so t squared. Beauteous. And there's not a whole lot you can do there, so you can leave that if you want to, or if you want to clean it up a little bit, it ends up being y prime equals, let's do like 2t, 3 to the 2t ln of 3, which is not super pretty, but that's okay, minus 3 to the 2t over t squared. Because there's no t in this part of your expression, like in front or in the back of it, this is really what you can have as an answer. Okay, just take a sec. Stay strong. The school year is almost over. You have like a month left. Get excited. Okay, back to derivatives. What I recommend, guys, for this question is have your other half of your paper open so you can see what the derivative of logs are. But I want to remind you that the derivative of any log is going to be 1 over the value. So if this was x, it'd be 1 over x times the natural log of 10, but in this case it's 1 over sine of x, because that is our value there, times ln of 10. But then you have to do times the derivative of what's inside here. It's kind of like chain, right? It is chain. So times the derivative of sine of x, so it's cosine of x. You could leave it as cosine of x over sine of x ln of 10, or cosine x over sine of x is cotangent of x. That's a cotangent over ln of 10. Beautiful, gorgeous, that is it. If you left it like it was originally, that's fine too. All right, I want you to try this next one, see if you can get it, but be careful, because what rule do you have to use? Here, I'm giving you a hint by drawing a little symbol. So pause the video, get an answer, unpause it, see what you got. All right, so hopefully you used the product rule. So you have to do first, which is the first part, times the derivative of the second. So be careful, because this is 1 over this whole thing, times the ln of your base, which is 2, times the derivative of that. So you end up with 1/2 x plus 1 to the negative 1/2. Then you have to do plus the second times the derivative of the first. So you can leave it like that for sure, or if you want to make it look a little bit nicer, you can do this. I did it as x to the 3 over 2 over 2 ln of 2 times x plus 1, because this is the same thing as that. So if you square it, there's only one of them. If you saw that, awesome, good for you. And then it's plus 3/2 log base 2 of radical x plus 1 times radical x. Technically, you can combine these if you want to into one big radical, but you don't have to. If you kept going, awesome, great, good job. Okay, anyway. So the next part is comparing, I'm gonna move that out of the way, comparing variables, whoa, and constants. Okay, so weird. However, what's cool is, what is that? E to the E. That is just a number. So what's the derivative? Yes, it's 0. Awesome. Okay. Now, the next one, I'm actually going to let you try it out a little bit. And then if you're feeling adventurous, try this, the third one, this one, that one. Just be careful with this one, because you're going to need some extra stuff going on, like multiple steps. So anyway, pause the video, see what you get, see if it matches. All right, so funny story. This is a number. So when you take the derivative, it's e to that whole power times the derivative of the power. That's literally 6x plus 0, just 0, because that's a number, right? So if you want to rearrange it, it's this, but you could have left it like e to the blah, 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 blah times 6x, right? The next one, think of just, it's a power. It's like x squared. You bring the power down and then you subtract 1. So bring the e down in front and subtract 1. Done. Beautiful. Don't overthink these. All right, next up, we got logarithmic differentiation. So just be careful, you have to use it when, you have to use logarithmic differentiation when your base and exponent are both variables. So just be careful. What that means is you must take the ln of both sides first, kind of like we have done before, although now this is the rule for it, okay? My recommendation is rewrite the ln, okay? Drop that x minus 1 in first, in front is what I meant to say, and then take the derivative. So what's the derivative of ln of y? Yep, 1 over y, dy dx, bringing it back hopefully. Then you have to do product, right? So first times the derivative of the second plus the second times the derivative of the first is 1, okay? You can rewrite that if you want to, or you can leave it as is. And then you have dy dx equals some shenanigans, right? Move that 1 over y. How do you do that? Oh, you multiply it to both sides. Cool. I simplified this a little bit, so I distributed the 1 over x and turned it into 1 minus 1 over x plus ln of x. And then remember, your last step is literally just plug in what y was. So dy dx just becomes dy dx equals whatever y is, which is x to the x minus 1. And then you just multiply it times 1 minus 1 over x plus ln of x. Now you can simplify that a little bit more, or just leave it. I would leave it. Just leave it. Leave it alone. Okay, try the next one on your own, please. All right, if you got that answer, pat yourself on the back, or someone else if they're near you. Have them pat you on the back, if it's not weird. So just feel free to keep this factored if you want to. That's fine. You can leave it as x times 1 plus x. I would definitely move this down, but if you had some form of this, that's good. If you didn't, just be careful that you are using product rule again. So it's first times the derivative of the second plus the second times the derivative of the first, and the derivative of that, as we've talked about, is really, this is really like x to the negative 1, so it's negative x to the negative 2. Okay, so tangent line. We've done this like a million bajillion times in different ways, except this time our base is the sine of x. So think about how we take any kind of variable to the variable exponent. It's what we just did, so that rule applies to these as well. So you have to be careful and do what to both sides first if it's a variable raised to a variable. Take the ln of both sides. So we have ln of sine of x to the 2x as well. That's the next that I needed to write there. Okay, so then apply some log rules. 2x ln of sine of x, okay? Now take the derivative, plug in the point to find the slope, write the equation of the tangent line. Okay, so take a little bit of time, and I want you to figure that out. So then you take the derivative, which is 1 over y times, product rule again. So first, derivative of the second, so 1 over sine x times the derivative of sine of x, which is cosine of x, plus 2, because that's the derivative of the first, times the second, which is ln of sine of x. Okay, then from there, oops, I forgot our 1 over y dy dx. Sorry. So then you have to multiply both sides by our y, same as before. So we have dy dx equals y times that whole big thing. So 2x times, this is really cotangent, so cotangent of x plus 2 ln of sine of x. Okay, so then from there, plug in your point. So x and y, so we get 1 times 2 times pi over 2, so pi. Cotangent of pi over 2, think about your unit circle, is 0 over 1, which is a 0, plus 2 ln of sine of pi over 2, which is 1. The ln of 1 is 0. So this whole thing ends up being 0. And if you have a 0 slope, that's a horizontal line, which means it's going to be y equals 1. Okay. Integrating an exponential function. Yeah, getting into the good stuff. Okay, so integration, you can kind of tell what it's going to be based off of what we already did. However, if you think about the derivative from what we had before, if we took the derivative of a to the x, it's a to the x times the ln of x. So to integrate that, we need to undo what we just did. So think about, instead of multiplying by ln of a, we need to do a to the x times 1 over ln of a. So remember, the derivative of a to the x was a to the x times the ln of a, right? So now we're undoing it with the integral. So a to the x times 1 over ln of a plus c. Okay, so it's really a to the x over the ln of the base is our integral. All right, so using that idea, let's integrate 2 to the x. Okay, I'm going to take our base, I'm going to just rewrite it. So the derivative of 2 to the x was 2 to the x ln of x. So the integral is 2 to the x times 1 over ln of 2 plus c. And you can leave it like that, or you can rewrite it, make it look a little nicer as 2 to the x over ln of 2, if you like that better, plus c. Okay, so the next one involves a little bit of u substitution. I'm going to help you set it up first. So try to make it look like that, if that makes any sense. So what I want you to think about is, first of all, think about what u is going to be. What do we already know the integral of, so that you can integrate easily if you have u instead of the other stuff? So take a second, think about what u is. Okay, and if you ended up with 3 minus x squared, that's a good idea, because if we did 3, or if we did 7 to the u squared, that wouldn't really help us very much. So instead, now we have 7 to the u, and that we can integrate. Okay, so that means that du is going to be 2 times 3 minus x times negative 1, so be careful because the derivative of negative x, negative 1, and then dx, and that's multiplication going on with the negative 1, okay? So it's really negative 2 times 3 minus x dx, okay? So there's no negative 2 in the original equation. However, there is a 3 minus x, so we can factor out that negative 1/2 because we want to cancel out that negative 2. And now we can integrate 7 to the u, because look, that's what u is, du. And then now we know the integral is negative 1/2 times 7 to the u times 1 over the ln of 7 plus c. And then you just want to plug back in. So I rewrote it so it's a little bit nicer looking. So I wrote it as -1 over 2 ln of 7. So I combined the 2 and the ln of 7 times 7 to the, now u is 3 minus x squared plus c. If you're still having trouble with u substitution, please, 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 please come and see me, because it's like a forever thing that you got to know how to do. So, all right, next up, I would actually like you to try this one. So the only addition to what we just learned is that now they're integrating between 0 and 1. So just be careful. Integrate both of those, plug them into your calculator after you're done, all right, and then check out what you get. Alrighty folks, hopefully you got what I got. If you didn't, check out what I did. So remember, the integral of 6 to the x is 6 to the x times 1 over ln of 6, and then minus 2 to the x, 1 over ln of 2. And then we plug in 1, subtract what we get after we plug in 0. Anything to the 0 is 1, so it's 1 over ln of 6 minus 1 over ln of 2, and then times what we got at the beginning. And you should get about 1.347. Okay, last of the kind of complicated stuff here. The next 2 questions after this are actually like algebra 2-ish, so they're pretty nice. However, this one, I want to help you set up the integral. We've done this a few times now, but now you're integrating between 0 and pi, as you probably already know. 3 to the cosine of x, sine of x. Okay, my hint on this question. To integrate, you're going to have to use some u substitution. So think about what you would like u to be. Okay, take a few minutes to figure that out. If you feel uncomfortable, keep on going. But pause the video, I'll have the answer for the u part, and then I'll have you pause it again if you're not sure to keep going. All right, so hopefully you figured out that u is going to be cosine of x, which means du is negative sine of x. So you have to do the negative integral to cancel out that negative sign between 0 and pi of 3 to the u, and sorry, this is dx, du, because du again was negative sign, which takes care of this baby. All right, now integrate. So we end up with 3 to the u times 1 over ln of 3. And again, it's between, and let's throw the negative in there, sorry. It's between 0 and pi. Okay, and throw the u back in there as well. So it's going to be 3 to the cosine of x times 1 over ln of 3 between 0 and pi. So then we plug in. You guys know how to do this part. So 3 to the cosine pi times 1 over ln 3. And then you want to plug in the 0, so 3 to the cosine of 0 times 1 over ln of 3. Okay, so then you plug that into your graphing calculator, and you should get about 2.427. All right, last kind of question we're looking at today is exponential applications. So you guys have seen these before. Just a reminder that if it's quarterly, monthly, yearly, whateverly, daily, your function is a equals p times 1 plus r over n to the nt. And a reminder, p is your principal amount, so that's 2,500. Your rate is your percentage, but it's as a decimal, so 0.05. And then t is 5 years. Quarterly is your n here to start, so n would equal 4. So your first part would be quarterly. If you plug in n equals 4, you're plugging in 2,500 times 1 plus 0.05 over 4 in this case, to the 4 times 5, because 5 was t. So you get about $3,205.09. I would like for you to try the monthly, and then if you're feeling comfortable with continuously, just a reminder, it's a slightly different formula. It's A equals PE to the RT, so a little different. So try those few, and hopefully you get the same answer. All right, so just a reminder, monthly means that your n is going to be 12. So everything in the equation stays the same except for the 4's. Okay, so you end up with a little bit more money. So So it ends up being $3,208.40. Okay, so a little bit more. And then if you try continuously, again, P is still $2,500. But now you're raising E to the 0.05 times 5. So it ends up being about $3,210.06. So again, that's the best deal, is compounding continuously, hence why banks don't usually do that. Okay, if the interest is compounded continuously, what is the rate at which the amount of money in the account is changing when t equals 0? So keywords here. Rate at which the amount of money is changing. What is that? Yes, it is the derivative. Okay, so using the values that we have in PERT, so A equals P e to the RT, when t equals 3, we're going to save for after we take the derivative. So first, let's plug in some values we know. It's going to be A equals 2,500, e to the 0.05 times t. But now we want to take the derivative of that, okay, because it's rate of change. So A prime equals 2,500 e to the 0.05 t, but times the derivative of that exponent, so times 0.05. So that ends up simplifying to about 125 e to the 0.05 t. Now we're going to evaluate it for when t equals 3, so plug in 3 for t. Okay, and you end up with your rate of change for that is going to be about $160.50 per year, because it is your rate at which the amount of money is changing when t equals 3. All right, last up, we got bacteria. Woo, bacteria. Okay. So the first two questions, they're just asking you to find the weight of the culture after a certain amount of time. What's cool is that Y is the weight and T is the time in hours. So think about what you're going to do with those three numbers. That's right. You're going to plug them in. So use your graphing calc, plug those in. If you can figure out the last question, more power to you. But pause the video for me. When you're unpaused, you'll have the answers. All right, so you get 100 grams, then 107.06 grams, and then 124.4 grams. If you want to try in 100 hours, you're going to see what happens to t as it approaches infinity, or the limit when t approaches infinity. So if you plug in really large numbers for t, hopefully you're going to notice it's approaching 125. You might also recognize that that is the coefficients divided, because the relationship that we used to talk about with rational functions, if your degree of your numerator equals the degree of your denominator, then you divide the leading coefficients. Now the degree of the numerator is t to the 0 power. This is a negative power, so the highest power here is also 0, so these match. So we have degrees that are actually equal here. Divide the coefficients, so 125 over 1 is 125. All right, folks, enjoy the rest of your day, and I will answer any questions that you have next class.